We'll straight away go to the next presentation. The presentation is on developing a thermodynamic material and study of kinetics of degradation of anthocyanin from local grapes. There are three authors, D. Ekanayake, KAP Amanda, and A. Tillekaratne.
Good afternoon to all of you. My topic is developing a thermochromic material and study of kinetic of degradation of anthocyanin from local grapes. As the name implies, thermochromic, the material change its color with the temperature. These type of synthetic thermochromic materials are used in many industries, mainly medical and food. These are few examples for the users. They are incorporated into the mugs and baby bottles, kettles, and food safety ensuring stickers. But there are few disadvantages of this synthetic thermochromic material. They are expensive and they have toxicity. According to researchers have found that currently available all thermochromic pigments at least contain one carcinogenic compound and they can cause environment pollution. Therefore, researchers have paid attention to find out naturally derived thermochromic material. As an example, anthocyanin. It is a glycoside derivative of anthocyanidin, a flavonoid, water-soluble, one class of flavonoid compound. At least 300 naturally occurring anthocyanidin present in nature. Let us look at the chemical structure of anthocyanidin. These R1 and R2 groups can be substituted by hydrogen, OHO or CH3 groups. Depending on that, there are several types of anthocyanidin. Few of them are cyanidin, malvidin and planogonin. This cyanidin present in a red cabbage, cherry and apple. Blueberry and grape skin has high content of malvidin and strawberry and radish has high content of planogonin. As said before, there are several types of anthocyanin present in nature. One example for the anthocyanin is cyanidin 3,5-diglycoside. This part represents the anthocyanidin group and this part represents the glucose molecule. This glucose molecule attached to the 3' hydroxy position of the anthocyanidin. The stability of anthocyanin mainly depends on the pH, temperature, light, co-pigmentation, metallic ions and presence of oxygen. In here, we are mainly focused to the effect of pH and effect of temperature. In a strong acidic aqueous solution, this flavanium cation is predominated and it diprotenoid and quinoid base is formed. Hydration of this flavanium cation result colorless hemicatyl form. Then it tautomerization and isomerization of the hemyl cation finally result pale yellow color chalcone. Temperature is strongly affect the stability of anthocyanin. The magnitude of the heating and the duration of the heating strongly affect anthocyanin stability. These are few products resulting from thermal degradation of anthocyanin. As examples, cyanidin 3-glycoside convert into a cyanidin and further heating result converted it into a fluoroglyceraldehyde. There are two main objectives of this research. Identification of the condition which enhance the stability of anthocyanin and extend the kinetic result for the thermochromic system. In order to continue the experiment, anthocyanin was extracted from the fresh grapes. To continue the kinetic study, it was in here 4 different temperatures, 4 different buffer system and 4 different solvents system was used. Then the anthocyanin content was measured using pH differential method. As an example, anthocyanin was extracted using water as solvent, then it kept at particular temperature and the pH of the solution was maintained at the particular pH. After some time, the solution was taken and it was divided into 2 portions, and one of the solution pH was maintained at pH 1 and the other one was pH 4.5. After that, absorbance was measured at 500 nanometers and 700 nanometers. This is the graph of the absorbance wavelength for water extract at pH 1 and pH 4.5. At pH 1 solution, this solution contained monomeric anthocyanin, polymeric anthocyanin as well as turbid. When we consider about pH 4.5 solution, it contained only polymeric anthocyanin and turbid. Therefore, to calculate the monomeric anthocyanin concentration, this equation was used. Malvidine triglycoside is a main type of anthocyanin present in fresh grapes. It shows lambda max around 520 nanometers. This is the equation for the first order kinetics, because the degradation of the anthocyanin follow first order kinetics, and concentration is proportion to the absorbance. Therefore, this equation can be written as ln AT divided by A naught equal minus KT. Then the degradation of the anthocyanin was studied using Arrhenius equation. All of these equations used for the further analysis. The rate constant was evaluated using ln AT divided by A naught equal minus KT. This black color indicate pH 8, then green color for pH 5, red color for pH 2 and blue color for pH 1. According to this graph and the data obtained, highest degradation rate can be observed in the pH 8 solution. As said before, in here we use 4 different solvent systems to extract the anthocyanin. Out of that, to find out the best solvent system, this graph was used. You can see at all pH values, the acetone show highest degradation rate, and compared to that, water and ethanol show lowest degradation rate. The activation energy can be evaluated using Arrhenius equation. According to this graph, pH 8 show lowest activation energy. That means it has the highest anthocyanin degradation rate. Using that kinetic study grade data as an application, in here thermochromic film was developed. To develop thermochromic film, we need some metrics. In here we use chitosan, agar and agarose as a metrics. But only chitosan give positive result. The following procedure was used to form a film, and the film was kept at different temperatures and the color change was observed. In a low temperature, the time taken to get the color change is very high. But when the high temperature, the matrix change its color very quickly. Finally, we can conclude that stability of anthocyanin strongly depends on temperature, pH and the solvent. Stability is maximized at low pH values, low temperatures and the presence of ethanol. Chitosan is an ideal matrix for the developing a thermochromic material. Noticeable color change can be observed in a chitosan anthocyanin film. Ethanol is a non-toxic material in small doses. Therefore, our results support the potential of developing food colorant based on anthocyanin from local grapes. These are my references. And thank you so much.
Thank you very much. And now the paper is open for discussion. I think it's very, yeah.
Okay, so you're developing thermochromic films. What applications do you anticipate in using your technology? Yeah, how do you commercialize it? What applications do you have in mind as target applications?
Support that this type of thermochromic film can be applied as a label in the commercial level. It can be attached into a food. Then, according to food, as known as food temperature change, according to that, this indicator changes color. Sticker changes.
So you're anticipating from 2 degrees to 30 degrees, is it? Did you say 2 degrees to 30 degrees, or what's the temperature range? What is the application temperature range that you're targeting?
In a commercial level?
Yeah. So you're applying it to food packaging, right?
Yes.
Okay. So what is the temperature at which you want to apply this? What is the range of temperature?
I think it is suitable for mainly dairy products. Normally dairy products should kept in a refrigerator, but if the temperature is below that level, this label changes color. Therefore, using that, consumer can get idea about the quality of product directly.
Good, I like it.